Welcome back. In this video we're going to be looking at how we can apply our acidity constants knowledge, pKa, pKb, Ka, Kb, to different calculations applying concentration to equilibrium position to determine the value of H3O plus in solution. Let's get started. We know now that for the reaction of a weak acid with water, we can give these equilibrium expressions, which we call Ka and Kb for weak acids and weak bases. The general formula being the HA plus H2O goes to A minus and H3O plus. A minus plus H2O going to HA and OH minus. This is the same as the one that we saw before, which said B plus H2O going to B plus OH minus. I prefer this one. Either way will work as a general equation. So now we have the expressions Ka and Kb, where the ions as products are put on the numerator and the concentration of the acid initially, the concentration of the acid is put as HA. So there are a number of mathematical relationships, as we've seen in the past with pH, that will apply to our Ka and Kb, and you should make a list of these as relationships that can help you with the calculations. These relationships are really important because they can help us work out concentrations of conjugate base or other things like that. So essentially, if we look at this, we can state that the Ka times the Kb is going to be equal to this expression times this expression, and we will get this H3O plus times OH minus, which we already know as Kw, which is 1 times 10 to the negative 14 moles squared decimeter to the negative 6. Okay, so for any weak acid and its conjugate base, we can write that Ka times Kb is going to equal Kw. If we know Ka, we can determine Kb, and so forth. But even more advantageous to us for working out calculations in real systems is the idea that we can then take the negative log to base 10 of each of these values. Okay, and we will get that the pKa plus the pKb is equal to the pKw. You can only use these for weak acids and bases. Okay, they can't be used for strong, but this means that you have a number of different tools in your kit for working out the concentrations. Okay, so this means that if we have a pH, we can work out H3O plus concentration. We can use pKa and pKb to find the relationships between things. So we know with strong acid calculations we've assumed that the initial acid concentration is equal to the H3O plus concentration because we essentially assume that ionization is complete. So if we were to consider the pH of a 0.1 mole per litre solution of hydrochloric acid, we say it is 1 because the concentration of H3O plus in this is going to be equal to 0.10 mole per decimeter cubed. Okay, we can state the hydrolysis reaction using the full forward arrow because we assume that hydrolysis is complete, and the Ka is going to be 1 times 10 to the negative 7. This coming from the fact that we know the Ka times Kb is equal to Kw, okay, and Kw is 1 times 10 to the negative 14 m squared, meaning that in a neutral solution, in the solution we're going to have 1 times 10 to the 7. The reaction proceeds so far to the right that it is valid to assume that the HCl concentration is equal to H3O plus concentration, and then we substitute this into our equation. With weak acids, we can't make this assumption. They only partially ionize, so we have no way of quantifying the H3O plus concentration. We can determine the pH using the Ka values and an assumption that the initial acid concentration is equal to the equilibrium acid concentration. Let's look at that in a bit more detail. So if we were asked to calculate the pH of a 1 times 10 to the negative 3 moles per decimeter cubed solution of ethanoic acid, remembering that ethanoic acid is a weak acid, and we've been given the Ka, we can then write the expression. So the equation for the hydrolysis of ethanoic acid is here, using our equilibrium arrows, which means the expression for this is going to be Ka. We know how to write that expression. We now have a numerical value for that expression from the Ka in the question. We also know that the concentration of the CH3COO- ion is going to equal the concentration of H3O+, because we get one CH3COO- for every H3O+ that is formed. It's a 1:1 ratio. So if we know that, we can rewrite the expression using H3O+ squared over the CH3COOH is equal to this. So now the only thing we really need to know is the concentration of the acid at equilibrium. We know that the initial concentration of CH3COOH is very only ionizing very small amounts. So the total is going to be the concentration of the acid plus the concentration of the anion, which is 1 × 10⁻³ . Okay, so from here, we know it only ionizes a small extent. So as a consequence of this, the concentration of ethanoic acid is said to remain virtually constant. So therefore, with these calculations, we are making the assumption that the initial concentration of the acid is going to be equal to the equilibrium concentration of the acid. So we can then take the concentration from the initial question and use that. So this is a key assumption in these calculations. We need to assume that the initial concentration of the acid is the same as the equilibrium concentration. Once we do that, we can then substitute that into our equation and solve for the amount of H3O+. So this is one taken all the way through. So we're back to this ethanoic acid. We've been given the Ka, same values as before. We had gotten this far with our expression. We can now substitute in the initial concentration into our Ka expression. We get that H3O+ squared is equal to this value, so the H3O+ concentration is going to be the square root. This means we'll have 1.32 × 10⁻⁴ moles per decimeter cubed. This value can now be plugged into our pH calculation and work out that the pH of the solution will be 3.88. Let's have a look at a few more calculations to sort of bed that down. This time we've been given hypochlorous acid. It's widely used as a germicide and bleaches in swimming pools. Essentially, this is where we get chlorine for swimming pools. It has a 0.25 mole per decimeter cubed initial concentration and a pH of 4.07. You've been asked to use this information to determine the acid dissociation constant, pKa, of hypochlorous acid. So this is going to be negative log to base 10 of the Ka value, and Ka we're going to get from our dissociation constant. First of all, we need to write the equation for the ionization of hypochlorous acid. It is an acid, so it is going to donate a proton, even if we don't know what this is, forming H3O+, and then we will be left with the conjugate base, which is just one less. So now I have my two ions. I have my initial concentration of the HOCl. So I'm going to write my Ka expression. All over HOCl, which I can simplify down because this is a 1:1 ratio. Sorry, 1:1 ratio. So these are going to be exactly the same value. So this becomes H3O+ squared all over HOCl. and we have a pH value. So the pH is equal to 4.07, so the concentration of H3O plus is going to equal 1 times 10 to the negative 4.07. So this is now going to be substituted up here. 1 times 10 to the negative 4.07 all squared over the 0.250 initial concentration. Now we can solve that in our calculator. 1 times 10 to the negative 4.07, and then we're going to square that. So squared, and then we're going to divide that by 0.250. And we're going to get the Ka is equal to 1, 2, 3, 4, 5, 6, 7, 2.9 times 10 to the negative 8 moles per decimeter cubed. Now that we have the the Ka, worked out our Ka, the question wanted us to find the pKa value. So pKa is equal to negative log to the base 10 of the Ka value. Again, we just plug that into our calculator. Negative log to base 10 of the 2.9 times 10 to the negative 8. And we get a value of 7.54 is the pKa. So these are fairly long calculations where we need to combine the information of our knowledge on equilibrium with our different equations for Ka, pKa, and pH, and bring all that information together. So the key assumptions that we make for these calculations are that strong acids and strong bases, the concentration of the ion is going to form the concentration of H3O+, okay, and that we assume that the initial concentration of the acid is going to equal the initial concentration of H3O+. With weak acids and bases, however, the assumption that we make is still that the ion, the conjugate base, is going to equal the concentration of the H3O+, because we're only ever dealing with single ionization steps. And then in the case of our initial concentration of the acid, this is going to equal the equilibrium concentration of the acid, so we will use that in our equilibrium expression because the ionization is so small. As Ka increases, the strength of the acid increases, but the inverse for pKa. So when we have a large pKa, we have a weak acid. That relationship is the same for a strong base. Where Kb increases, we see an increase in the base, and pKb increases means that the base becomes weaker. These are, of course, linked to equilibrium constants. So for a large K value, we know the reaction is far to the right, whereas a small K value means that it has not moved far from the reactant side of the reaction. Okay, with Malus calculations, remember it's practice that allows us to consolidate these ideas. So I recommend that you go to your textbook, practice some of these style calculations, and also the worksheets that I have put up online, and I'll see you in class.